Hi, this is Mrs. Roble. This is part 2 of the Standards and Measurements unit. And what I want you to do is watch a short video before we talk about some important concepts about measurement. And just pay attention to what this person is talking about with a piston and a cylinder.
Hi, this is Jeff at Slavens Racing. This video is about piston to cylinder clearance, how to measure it, and about ring end gap. So what is piston to cylinder clearance all about? Well, obviously the hole here has to be a little bit bigger than the piston or the piston can't go up and down. And so what is that optimum clearance? Well, that's determined by the manufacturers. And for this size of a bore on this style of a cylinder with a Nikasil coating, I didn't look it up on this, but I'm pretty sure it's probably around 1.2 to 1.5 thousandths would be on a brand new fresh cylinder, with probably up to 3 thousandths being their tolerance. You know, they can actually go bigger than that, 4 or 5, but that's starting to get pretty loose. And when pistons get loose, then that's when you get cracked pistons. You know, they'll crack up the skirt and break a chunk off and blow those pieces in the bottom and sometimes take the rod out with it. So you don't want to let them get to that point. So, and why we have different clearances for different types of engines is because of how they're built. I mean, this is aluminum and this is aluminum, but they're different types of aluminum and they're different thicknesses, and so they swell, they expand at different rates. So when the engine heats up, this expands and the piston expands. And they calculate those rates and figure out what it's going to take to keep the engine alive. And so the clearances I mentioned before are pretty typical of a cast piston, which is what this is. With a forged piston, like a Wassner or a Wiseco, then the clearances need to be larger because...
Okay, so I'm going to pause that there. So he's essentially talking about two pieces of equipment in an engine. And notice they're different metals, different thicknesses. They have different requirements for their separation. So the bore that he was talking about with the cylinder, if it's too big, it's going to cause the cylinder to crack. I'm sorry, the piston to crack. So obviously when you are machining objects like that, you have certain tolerances or certain targets that you have to make. Now you might ask yourself, what does this have to do with chemistry? Well, with chemistry, we typically are concerned about accuracy. So accuracy is how close the measurement is to an accepted value. So he was talking about the cylinder being a certain opening measurement, and that if it was too big, it would cause the piston to crack. So it's in the manufacturer's best interest to be accurate. Now, precision is something that students get a little confused about. You know, they think if you're precise, that must mean that you're good. Well, the problem with precision is that you could be good in the sense that you keep getting the same type of measurement, but that measurement is nowhere near the accepted value. So you could be precise and not accurate, and it's important to pay attention to that. I'll show you an example in a minute. Now this is something that you will deal with in chemistry throughout the year. This is called error. So error is essentially the experimental value, the value that you get in lab minus the accepted value. So you have to look up what is the accepted value for your measurement, and you're going to compare it with what you determine experimentally. Now with this next calculation, you're going to find that this is something you're going to do over and over again. Sorry, I made a mistake there. I'm trying to get my pen. Okay, so error, that's your that's your lab value minus the accepted value. Notice that it goes in here, and there's two lines on either side of it. This is an absolute value. So you'll take your lab value minus the accepted value, and you'll take the absolute value. So if it's a negative number, it becomes positive. And notice that you essentially divide it by the true values or the accepted value, and then multiply it by 100. You will do this over and over again throughout the course of the year. So I would get to know this equation very well because it'll become your friend when you do a lot of experiments in chemistry. Now, what does this mean to you? So here we have a student, and they've essentially taken measurements. And if you look at this first set of measurements here, we've got 1.7, 1.69, 1.71. Would you say that these measurements are accurate or precise? Now, if you look up here, the accepted value is 1.59. So, would you say this person was accurate or precise? More likely they were precise but not accurate because their numbers were not close to 1.59 as opposed to like student B or student A. So you could almost argue that student A was both accurate and precise because their average was 1.57, which was not far from 1.59. Okay, now, hard to believe, but you do have more rules about significant figures that I have not discussed with you yet, so just bear with me here. Counting numbers. Okay, so counting numbers is essentially if you have 30 students in a room, that would be a counting number. So that number 30 has infinite number of significant figures. So that means that that number essentially would have no limit to the number of significant figures. Now, like I said, this is 30 students. This is a counting number. This is not a measurement, okay? So you have to be careful with that. All non-zero digits are significant, so that means anything from 1, oops, sorry, let me go back. I'm trying to get my pen. So that means anything from 1 to 9 is considered significant. Any zero between non-zero digits is significant. What does that mean? Well, that means that if I have a number like 1005, how many significant figures is that? 4, okay? So we count each digit as being significant. So those 2 zeros in between the 1 and the 5 are considered significant. All zeros to the right of a decimal point and a non-zero digit are significant. Okay, so what does that mean? So I have 1 point, that's a decimal place, sorry, it's not very neat, 0, 0, 0. Okay, so 1.000, how many significant figures is that? 4, okay? So all those zeros that are to the right of decimal place are considered significant. Leading zeros are not significant. Okay, this is where it gets very confusing for students. So you have to remember, please, this is a really important rule because some people tend to forget about this. So if I have 0 point, what's decimal place, 0, 0, 0, 3, how many significant figures is that? 1. Okay, you only count that non-zero digit. You don't count any of the zeros that are to the left of that number. Okay, here, this is a little tricky. Zeros to the right of a non-zero digit, so any number 1 through 9, and left of an unexpressed decimal point may or may not be significant. This rule tends to be kind of nebulous. The good news is I am not going to use this, but you may see this in older textbooks or maybe older experiments where there's a bar above the zero. So these zeros would be considered trailing zeros, like it says at the end there. I know it's a little confusing, but like I said, you may see this in older textbooks. A better way of doing this would be using a decimal point. So what does this mean? So you have the number 1, 0, 0, 0, 0, 0, 0 decimal place. Okay, so I'm going to put a comma here and a comma here. What I've done essentially with this number is I've made that last zero part of the significant figures. So if you had to look at that number, how many significant figures would that be? 7. So because I have that decimal place to the right of those zeros, all those zeros are significant. Okay, with trailing zeros, the best way to deal with it is to use scientific notation. So instead of having what I had last time, this is where it gets a little crazy, I know. But if I wanted to express that as scientific notation, I would do 1.1, 2, 3, 4, 5, 6 times 10 to the 6th. So the number 6 rule on the previous page, the way around that would be to write it like this. And it's the same number that I gave you for rule 7, okay? So that is your way of expressing all zeros as being significant. And it's still 7 significant figures, just to let you know. Okay, so once again, we talked about multiplication and division. And remember, we're looking for the number that has the least significant figures. We're not caring about how many digits are to the right of the decimal place. So we're just looking at the number of significant figures. And notice that in this equation, or this problem here, 100 meters only has one significant figure. And that catches a lot of people, okay? Now the only way that this actually would have, if I put a little decimal place right here, okay, then that would be 3 significant figures, and then I could use 900. But because that's not there, your answer is going to be 1 significant figure. Okay, notice how if I add the decimal place, now both numbers have 3 significant figures. I have to put a decimal place to the right of that last zero to make it 3 significant figures. I know this seems kind of tedious, but this is the best way that people have come up with to show that each number is significant. Here we go. Okay, so how many significant figures do we have to deal with? Notice on the left, the 9.0 is only 2 significant figures. That means that the answer has to be 2 significant figures. And notice that we have to use scientific notation. That's the best way to essentially show that there's 2 significant figures. Please remember, this is not considered significant. That is a placeholder. Just the 9.0 is considered significant. Okay, this is just a review about addition and subtraction. Here we have 2 sets of numbers. The question is, what do we do with the remainder before we express our answer? Notice that there's only 2 significant figures here. You only count the 1 and the 2, so therefore you have to round to 2 significant figures. So your answer, I'm sorry, not round to 2 significant figures. It has to be rounded to 3 significant figures. I apologize. So your answer has to have 3 significant figures because that last digit is not significant. Okay, here are a series of problems that I want you to do for homework, and I'm essentially going to check them with the quiz that you're going to get when you get in tomorrow. So make sure you practice these, and you will hopefully pick the right answers for the quiz.